All right, we'll continue now. It's like food energizes the class. Cup of coffee and something from the deli counter, and now everybody's energized. Right. So what we're going to have a look at now is the next chapter, integration. And in fact, because the first two lessons are quite short, I think what we could try to do is have 3 small lessons rather than 2 normal lessons, because lessons 1 and 2 are actually very straightforward. So what exactly is integration here?
Reverse derivative.
Yeah, it's like a reverse derivative, antiderivative, yeah. So for example, note if you have a function like x squared and you differentiate that, you end up with 2x. So there must be some way of going backwards, some reverse process. So the reverse process we can just call an antiderivative. So if you anti-differentiate 2x, you end up back with x squared. What's the notation for this? So the derivative of x squared is 2x. And the way we write antiderivative is like this. We put it in between these two symbols. So the antiderivative of 2x is x squared. Now there's actually a small complication we'll get to in a moment, but I'll just let you write this notation down. You can call it an antiderivative, or you can call it an integration. Both are fine here. So just write this down. We'll talk a little bit more about this.
So you have to write the dx.
You do, really, yeah. I know. Okay. Got that? Yeah? Yeah. But there's a small problem. So, for example, if you have x squared plus 1 and you differentiate that, you end up with 2x. But we were just told a moment ago the antiderivative of 2x is x squared, not x squared plus 1. And this is a problem with antiderivatives. Because the derivative deletes the constant, you can't get the constant back. You've lost the constant in the process. So when you integrate, there's some constant which you don't know that exists. So to be more precise, the antiderivative of 2x is x squared plus some constant we don't know what it is, that we lost when we differentiated. Now there are ways to work it out, but just for the first class we won't concern ourselves with that. So what we need to have a look at now is what are the rules? So what are the antiderivative rules? And really, they're just the reverse of all the derivative rules. So let's put this together in a table now. Can I scroll down?
Yes.
Yeah. Okay, so here's our table here. Here is our function. And then here is the integration of the function. So let's start with something simple. Let's start with just a plain constant. So you learned that the derivative of kx is k.
Yeah.
So therefore the antiderivative of k must be kx with the plus c. Yeah? So can you see it's almost like a reverse table. Now, on to a more complicated one. If you have xn, now, if you think about the derivative rule, it was bring down the power, reduce the power by 1. Yeah. So now the opposite must be increase the power by 1 and multiply by the power, or divide by the power. So here it must be n plus 1 over n plus 1. Now you can test this out. If you differentiate this, you're supposed to get xn, and you do. Okay. Sin x was minus cos x, and cos x was sin x. And what about integrating 1 over cos squared x? What was that? That was the derivative of what? Tan x. So therefore the antiderivative of 1 over cos squared plus x must have been tan x. What about 1 over x? That is log x. Now you might say, well hang on, I have a rule for 1 over x. I have it earlier. xn. But there's a problem. In this, n can't be minus 1 because you can't divide by 0. Yeah? Couple more. So we haven't talked about e. So if you have e nx, that would be e nx over n. Oh yeah, and all of these have plus c's. No, that's the derivative.
No, the derivative would be NENX, but then
yeah,
you would divide.
Yes, divide instead. I think that's all of them. See, it's just some constant you don't know. You have to leave it as a constant, I'm afraid.
But there is a way of...
Yeah, which we'll do now in one moment. Yeah? Got that? Copy this table? Let's have a look at some examples. Okay, actually I can write the examples here. Let's say I want to integrate, I don't know, 1 plus x squared. Well, what does 1 integrate? According to the first rule, it becomes 1x, which is x. What does x integrate? Yeah, according to the second rule, it'll be x squared over 2, and then the next one will be x cubed over 3 plus c. Okay, let's try integrating 4x plus 5x squared dx. This one would integrate to 4x squared over 2, and then this one would become 5x cubed over 3 plus c.
Sure.
Yeah.
Couldn't there be a constant each time you integrate it?
Yeah, there it is there, plus c. Oh, you mean on each one? Yeah, but you can group all of them together and just say in total there's a single constant at the end. You're right, like if this one had a plus c and a plus c, well then at the back you have plus ccc, which is the same thing as saying plus a constant.
But the constant could be not the same, so how could you...
Yeah, but you can group them all together, you know? Like if I said to you the answer is x squared plus 3 plus 2, you would say, why are you being ridiculous, Stephen? The answer is x squared plus 5. So you don't care about the individuals. Just like life. Okay, so continuing now. Let's do a little bit harder one here. I'll let you try this one. Integrate 1 over x plus 1 over root x. Alright, I'll give you a minute to try this example. So there's the third example. Give that a try. See if you can do it. Got answers? Yeah. Let's have a look here. Okay, so the first one integrates to log x. Now, the problem with 1 over root x is you first have to change it to x power minus a half. And now you can, so now you can integrate. So it's log x plus, you increase the power by 1, so minus a half plus 1 is a half, and then you divide by a half plus c. And if you like, you can write the answer like this, log x plus 2 root x plus c, if you like. Okay, so now we said, yes?
I know it's a stupid question, but why 1 over square root of x is not then square root of x?
No, that's not a stupid question, actually. No, that's actually a good question. That's actually something a few students think, that because 1 over x becomes log x, then why doesn't 1 over root x become log root x? But the thing is, the rule is only for exactly 1 over x. Do you know what I mean? Like, there's no flexibility. With these rules, you have to match them perfectly. So, for example, you might say, oh, what about 1 over x squared? That should be log x squared. No, because the rule is only for 1 over x. So, there's no answer other than the rules have to match it perfectly. Now, you could have something like this. What about if I say integrate 1 over 2x? No.
2 ln x.
No.
Half
A half log x. Because you can change this into integrate a half times 1 over x. And that becomes a half log x. You see? Not log 2x. Yeah.
What about x is the same as x is by minus 1, right?
OMG, Mubarak, I just told you in the table, you can't have n minus 1 here.
Yeah, I know that.
Then why are you asking me?
I'm asking why can't we have it?
Because then you'll be dividing by 0.
Yeah, I know, that's what I'm saying, like math is not correlated. Shouldn't you be able to like that?
I know, Mubarak, don't make my life difficult, please. What? Do you really have a question? What's your question?
Like, because math is supposed to be able to like you can use multiple ways, but like now you can't. Because it makes sense if you use the other way.
Yeah, you have multiple ways, but you never have at your disposal the wrong way. Do you know? Right? Like, there's many ways to get this far, but you can't get there the wrong way. You can only get there the right way. And changing it into x minus 1 is not the right way. Yeah? Because then you'll divide by 0.
Sir, can that be also log of radical x?
Yes. Yes. Okay, Mubarak? Is it? Are you just trying to troll me, or like, I don't... Okay. For this level, Mubarak, for this level of integration, there really usually is only one way. When we move on to the more advanced stuff, especially in semester 2, we'll start to see questions where we could actually look at multiple approaches to the integration. But at this level, it's just, there's the problem, there's the tables, and just keep it like that. Okay, let's find the C. Because I said earlier we could actually figure out the C, but we need to be given more information. So as an example, suppose I said to you the derivative of some function is 2x plus 1, and I ask you to integrate to figure out what the function is. So what is the original function if I have the derivative? It's x squared over 2x squared over 2, which is just x squared, plus x plus c. Now the only way to figure out the c is that I must tell you something about the function, a value. So suppose in addition to telling you its derivative is 2x plus 1, I also tell you the value when x is 1 is 3. I've now given you enough information to figure out the c, because apparently f of 1, which is 1 plus 1 plus c, should equal 3. So therefore, c is 1. So the answer is the function was originally x squared plus x plus 1. And is the derivative 2x plus 1? It is. And if I put in 1, do I get 3? I do. So this is definitely the solution here. So to find the c, you must be given a point, a value. I think they've only done this in the exam in semester 1 once, where they asked you to find the c. Very often they just ask you to leave the c in it, and very often students forget to write in the plus c and lose a mark.
So you just substituted 1 with x?
Yeah. Yeah. Okay, can I scroll down? No? Yeah? Got this? Got this? Okay. So like I said, we're going to have 3 smaller lessons because the first 2 lessons are not so big, especially the second lesson. The second lesson is even less than this lesson, if you can believe that. So only until 11:35, and we'll start the next lesson. I'll give you some questions to practice. So from number 1, I want you to do a linear, a constant, a cubic. Yeah, that will do. And number 2, I want you to do a B, C, a D, a G, and a J. And number 3, just A. Okay, try these now, please. Yeah.
I know most of this answer about this. I just want to ask again to make sure.
Which one?
It's the one where it was 1 over radical x. Does that mean that any, if x was the denominator and it would have like a power of anything or a coefficient of anything, so you write it as the coefficient log x or log the power x?
I'm not sure I understand your question. Give me an example.
So
integrate.
1 over radical x, the same thing.
Yeah.
Could we write it as log radical x? Yeah.
Right. Amjad, he's asking me this question. Didn't you ask me this question?
Yeah.
You asked me this. Yeah. You answer for him. Because he asked me that exact question.
You have to be exact to the...
Yeah. You can't have any difference. There's no flexibility. That's not true. The only flexibility is you're allowed to pull constants out. So for example, if there was a 4 here, you could pull the 4 out in front and multiply your answer by 4. But it's not log here because it doesn't match up with log, which is 1 over x. Yeah. So there's, apart from pulling constants out in front, there's no flexibility.
Okay. But isn't 1 over radical x okay, but this is 1 over radical x, 1 over radical x all to the power of minus 1.
1 over root x is 1 over x.
No, is equal to radical x all to the power of minus 1.
Root x power minus 1.
Yeah.
Correct.
And we know that x to the power of minus 1 is log.
Yeah, but this isn't x to the minus 1. This is again root x. It needs to match exactly. No flexibility. No flexibility. Yeah.
Wait.
What?
What about you change radical x to x?
1 over x a half?
No, yeah.
Yeah.
And then x. Yeah, you can do it like that. X half power is equal to
X half power minus 1.
Still the same thing.
Still exactly the same thing. You can't, that doesn't become log.
No, and then multiply half by infinity.
Yeah, which is what I didn't. That's what I did. That's what I did when I did this one. Yeah. that's literally what I did. You just figured out what I showed you. Congratulations.
To the first and last?
Is that which rule?
No, they're right there. Oh.
Oh, I think I know it. Is it the AX plus B? Which
No,
one?
but if you have okay, and if I want to x dash, and if I want to remove the dash, I put percent.
Yeah, that's what I did in the last one. That was kind of my idea here. To remove the dash, I integrate. Yeah. No, but thank you, because that reminded me. There is one rule I forgot to give you, which is in the formula book, and it's this one. So if you want to add this to your table, please, it's 1 over ax plus b. So it's an extended log rule. This integrates to 1 over a log ax plus b plus c. So if you can add that to your table.
What would this look like as an actual question?
Oh yeah, they ask you, integrate 1 over 2x plus 3. So the answer would be a half log 2x plus 3 plus c. Yeah. Oh, is that the list of questions? No, let me zoom out a bit. Which one? 1 over a? Oh, I haven't proved the formula. The proof next semester. To be continued. Dun, 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 dun.
Sir, I'm just wondering, why does NCP go so in depth into calculus when it's not really used in the medicine like this? Like, it doesn't go this depth into medicine.
Yeah, the problem is... Well, can I close this? I need to close this.